Good morning, everyone. I'm very glad to see you back today. Yesterday we did chemistry, so today we're going to move on and we're going to do a little bit of physics, right? So if you turn to page 10, we are going to look today at work, energy, and power. Now, some guys find work, energy, and power very difficult. It might be because you've got a little bit of problems with components that we did in grade 11, right? It might be that there's a lot of different memos because there's different ways to do things. And then you are taught a specific way in class, and then you come to the memo, and the memo looks different. Right. I'm going to try to show you today why the memos are different. What is the different ways that they approached it? So we're going to look at work, energy, and power, all of that, everything you have to know about work, energy, and power, and then we're going to just look at what happens when I put the momentum equations with that. Which one do I have to choose if I'm doing bigger problems? So we're starting out on grade 10, and as always, we're starting out with a definition that you've already learned by heart. Hey? We talked about work done. Now, if you look at the definition there's some unexpected things in a definition. And when you learn a definition, go and look at the unexpected, because that's the thing that you're going to forget. So if you look at this one, it is the work done on an object by a constant force. Now, there you have constant force. That is a little bit unexpected. Constant force is F delta x cos theta, where F is the magnitude of the force. There's something else that you have to look at, magnitude. Delta x is the magnitude of the displacement, and theta is the angle, and what is important, which angle? The angle between the force and the displacement. Now, learning the definition by heart is one thing, but applying it is something else. So we have to know how to apply it. So if you take say, for instance, a crate on a horizontal plane, and you are pulling it to the side with a force F, you're pulling it 3 meters, say the force is something like 10 newtons, and they ask you, what is the work done by this force? Then we're going to say, the F now is that applied force we are working with. Delta x is the displacement, and then you have cos theta. So the force that is applied is 10. No components, nothing. We're using the magnitude, and the magnitude is 10. Fine. Delta x, how far is the displacement? 3 meters. And then you get to cos, and then we get to the angle. And what is the angle? It is the angle between the force and the displacement. So you put your pen in the direction of the force, and you turn it until you get to the displacement direction. Which is the displacement direction? It's also to the right. It's being displaced to the right. So how far do I have to turn my pen? Nothing. So now the angle is 0. Right. And there's a few things, if you know it, that make it easier. What is cos of 0? 1, yes. And cos of 90? 0. And cos of 180? -1. It helps if you have that in your head, because then it helps you to know. You don't even have to work out the cos theta. You know immediately it's 1. It saves you calculated time, but also it helps you to understand better. Now we get an answer of 30 joule. Now if you get 30 joule and it's a positive, what does that positive imply? No, not direction. The thing about energy that we measure in joule, it is a scalar, it's not a vector. If you go to the shop and you buy an energy bar, do you buy 340 kilojoules right? Huh? No. Energy doesn't have a direction, right? Otherwise, you would have a problem if you're going to run a marathon. Just make sure you always buy the forward ones, hey? Energy doesn't have a direction. So energy's got no direction, but now we're doing work. And now we have a positive and negative. What does it mean? If it's positive, it means we are putting energy into the system. We're making the energy of the system more, right? So if you do the same thing now for the frictional force being to the opposite side. Let's say we've got a friction force of 1 Newton. Now I'm going to say the work done by friction will be the frictional force delta x cos theta. And now the whole magnitude of the force, 1. The displacement, 3 cos. And now I put my pen in the direction of the force I'm working with, and I turn it until I get to the displacement. How far am I turning it? 180. And what do we know about cos 180? It's just minus 1. So this will end up as minus 3 joule. Right, what is the minus? It does not mean in the opposite direction. It means this force is removing 3 joule energy from the system. Is that right? No. Good. So this was easy because it was in the horizontal plane. Let's take one where we do the same thing but take a force that's acting at an angle. If we take one that's acting at an angle of, say, 30 degrees there, if, let's say, 100 newtons, and we've still got a frictional force of, say, 20 newtons, and now I'm moving it 3 meters, now we can do the same thing. They can ask us, what is the work done by the applied force? There's always F delta x cos theta. If it's the work done by the applied force, that F is the applied force, and that is 100. And you don't go working out components. Go back to your definition. The definition say the magnitude of the force. It doesn't say anything about components, right? You use the whole 100 newtons. And then delta x is the displacement, 3 meters. And then you get to cos, and that angle is between the force and the displacement. So put your pen in the direction of the force and turn it until you get to the displacement. How far are you turning it? 30 degrees. Right. And then you get a positive, no, I don't even have my calculator with me, a positive joule. Right. What does the positive mean? It's putting energy into the system, right? It's putting energy into the system. So whenever they're asking work, go and check the work of which force. You have to know which force you're working with. It's not always the applied force. It can be the frictional force. It can be the normal force. It can be the gravitational force. So if you look at this one, gravity is working down and the normal force is working up. What is the work done by gravity? Now, once again, you have to have the force, the displacement, and cos theta. Now, you will have the force, you will have your 3 meters, and you will have cos. What will be the angle for the gravitational force? Put your pen in the direction of the force and turn until you get to the displacement. How far am I turning? 90. And what do we know about cos 90? It's 0. So whenever you have a force that is perpendicular to the displacement, immediately the work done by that force is 0. Right. And remember, don't just write 0. You still write 0 joule. Just remember to keep writing the joule. Now, how about the normal force? What will be the work done by the normal force? Also 0, because it's also perpendicular to the movement. Right. So whenever you do that, remember, for the Department of Education, you don't even have to write the forces if you add them together that are 0. Something that's 0 you don't have to put in. But this you will have to work out if they ask you. Everyone happy? Right. Now, we're doing one on an inclined plane. And that's the one that's a little bit more difficult. So I put it for you on page 11. So let's just look at that. And now we're looking at one where we were working with an inclined plane. Now, I said in the example, a crate with a mass of 10 kilograms is pulled 4 meters up an inclined plane. So I'm pulling it up 4 meters, right? The angle with the ground is 30. And that's another thing you have to take away from this. As you read, go and check if what they give you in this wording is in your picture. If it's not in the drawing, add it to the drawing because it's easier afterwards to see in the drawing the information that you need, right? So The 4 meters was not there, and I put it over there. Inclined plane makes an angle of 30 degrees. That is there. The crate is being pulled by a force of 180 newtons and experiences a frictional force of 10. So that will be in the opposite direction. And now I ask you, calculate the work done by each of the forces working on the crate. So let's start with the first one. We start with the applied force. If you look at the applied force, it's acting in that direction. So the work done by the applied force will be F delta x cos theta. F is now the force 180, easy. Delta x, the displacement was 4 meters. And now we have to look at the angle. And how do I get the angle? I put my pen in the direction of that force, and I turn it until I get to the direction of the displacement. Where is it displaced? It's displaced in that direction. So how big an angle do I have to need? 0, nothing, right. And then you get plus 720 joule. And what does the plus mean? The fact that it's positive tells you this force is putting energy into the system, right. Let's go on to the next one. If you look at the next one, now we're working with the frictional force. Frictional force, it's 10 joule. The movement, the displacement is 4 meters, and then once again, I put my pen in the direction of the force I'm working with now. I'm working with friction. It's working down. And then I turn it until I get to the displacement. And that is 180. And what do we remember about cos 180? Yes, minus 1. So that gives you minus 40. And what does the minus tell you? That frictional force is removing energy. Right? It's removing energy. It will be slowing down the system. Right, and then we get on to gravity. Now, this is actually, with an inclined plane, gravity is the one that is difficult. Right. Now, if you work according to this definition, I'll show you the alternatives later on, but if you work according to the definition, we said the work done is F delta x cos theta, and we're working with gravity. So remember, not the mass. It's the mass times 9,8. That's one of the things that you get wrong. Then times the displacement, that is 4. And then cos. And now, what do we have for an angle here? The angle is the difficult one. What do I have to do? I put my pen in the direction of the force. And then I turn it until I get to the displacement. So what do I need? I need that angle. Now, if you think back, and this is where you have problems because you forgot about grade 11, right? With grade 11, we worked out the perpendicular force, and then we said this one, this angle over here, is the same as that small angle over there. Right, let's just go back and see why that is. If I extend this one, then I get a 90-degree angle down there. So if this is 30, and that is 90, and the inner corner should give me 180, that means that top one, 60. And then those two should together be 90 because they're perpendicular to each other, and then that gives you that one as 30. That was how we said that was 30. So that is grade 11. And now, what do I have to have? I have to have the whole one. So it's the 30 plus the 90 on that side. So whenever it's moving up an inclined plane, that one will be the bottom angle, the theta will be 90 plus the bottom angle. Right. Because it's always, the bottom angle is that one, and now I have to add that to the 90. So if it's moving up the plane, the angle will be 90 plus, and you use the whole gravitational force, no components. Right. How about moving down? Let's just take one where we say it's moving down. If you have that one, and everything is moving down, if it's moving down the plane, that angle was 30. Now, if it's moving down the plane and you want to work out the work done by gravity, we say, okay, what force are we using? We are using the gravitational force, so you work that out. Then delta x will be the displacement. And now the difficult thing is that theta. Right, so let's take a small break, and then you can work out what should theta be in this one. Hang on. Now I'm just showing you this inclined plane. And if you've got an inclined plane, we are going back to the definition that we had on grade 10, and we're saying when you want to work out the work done, you have to have the force, the displacement, and cos theta. And theta being the angle between the force and the displacement. So what we did, we said to work out the work done by gravity, if this thing is sliding down the plane and you want to work out the work done by gravity, the formula is W is F delta X cos theta. And that F is whatever force you're working with at that moment. So at the moment, I want to work out the work done by gravity. So the force must be the gravitational force, m times g, right? And then delta X is the displacement, but just the magnitude of the displacement. So there's no plus or minus. It's just if I am moving it 4 meters, then you have to put in there, that was m times g, 4 meters. It's just the magnitude of the displacement. And then you get to cos delta X. And in your definition, they tell you that angle must be between the force and the displacement. So we put our pen in the direction of the force we're working with at this moment and turning it until you get to the displacement. So how far am I turning it? Now, if you think back, when we had a horizontal force, a horizontal plane with a force like this, we said if we work out the work done by the applied force, we put our pencil in the direction of the force, we turned until we got to the displacement. So there you had to turn it 30 degrees. We said if we worked with friction, friction is in that direction. So you have to turn it from there right over to the displacement. So if it's moving in this direction, that's the displacement from the force to the displacement. You had to do that, and so for friction, the work that you do is always cos 180. It's always in the opposite direction, right? And if you work with gravity here, gravity was perpendicular to the movement, and then you had cos 90, and cos 90 is always 0, right? So then we went to the inclined plane, and when we got to this one, we said on an inclined plane, if you're working with the force that is applied, then that force is in the direction of the movement, because this thing is moving up the slope. So there you had to use cos 0, because the force was in the direction of the movement, right? And then we got to friction, and with friction, we said friction is working down the plane, but the movement is up the plane. So how far do I have to turn? 180 degrees. So there, it was cos 180, right? So still on page 11, we now work with gravity. And we said gravity is working straight down. And if you want to have the angle that you have to use here, remember the angle is between the force and the displacement. So you put your pen in the direction of the force and you turn until you get to the displacement. So over here it would have been 90 up there plus that angle that we in grade 11 said is the same as the bottom one, which is 30. So whenever it's moving up the plane, then the theta that you will use is 90 plus the bottom angle. So no components, no components. We're using the whole magnitude of the force and the whole magnitude of the displacement. And then we have to just make it everything right by using the correct angle. So if you were going up the slope, then the angle was 90 plus the bottom angle, because you had to have that whole one over there, right? But now in this new one, we are moving down the slope, right? And that's the one I asked you to look at. We are now working with gravity. We want to have the work done by gravity, but gravity is working like this, and the displacement is now down the plane. So I put my pen in the direction of the force and I turn it until I get to this displacement. So what do I need? I need that as my angle. Is that right? Okay. And what is that angle? Well, same thing we did now. This is 90, that is 30, and together they must be 180. Right, so that one will be 60. Or what we did before is we said that one is also 30. Remember, it repeats over there. So what you can say is when you're moving down the plane, then theta will be always 90 minus the bottom angle. Right. So if you are moving up the plane, then theta should be 90 plus the bottom angle. But if you're moving down the plane, then you're looking for that angle, and that will be 90 minus the bottom 30. Okay, and that makes it easier. Right. Okay. So that was for gravity. And now the very last one we have there is the normal force. So for normal force, it will be normal force, displacement, and then cos. And between the normal force and the movement, the angle is 90. And cos of 90 being 0 will give you no change in the energy of the system. Right. And remember, we also said if something is positive, if the work done is positive, it means you're putting energy into the system. If the work done is negative, it means you're taking energy out of the system. Like friction, it's moving, it's working against the system. It's taking energy out of the system. Right. Okay, so let's go back to page 10. So we've now looked at just the definition and how we apply that definition. We said we're working with a constant force. Why? There's only one space to put F in. So you can't have a changing force. You have to have a constant force. So this is the unexpected thing in the definition. We're just going to remember that. Okay, and then we also said, remember that the work done is a scalar. So if it's a scalar, it's got no direction. And if it's positive, then you have to say energy is put in. And if it's negative, you say you are removing energy from the system. So we're up to there. So now what are we going to do with all this work that we worked out? We're going to use it to get the net work done. And what's important is there's two different ways to do this. And sometimes you get confused. So the two different ways is the first method that you can use is you can get the net work done by adding all the separate works that we've worked out now, by adding all of them together. So you work out the work done by gravity, by the frictional force, by every single separate one, and then you add them all together. So there you haven't used components at all. We use the whole force every time. Right. The second way, and this is the way that you will do if you were great with components in grade 11 maybe, is to work out F net, and then to use F net in the same equation, but now it's the net force, and just remember then the angle, you have to work with the net force's angle as well. So we're going to do one of these. Right. So you get the net work done by adding the separate ones, right? That's one method. Or working out F net first, and then getting from that the work done. Right. Now, let's do that. If you turn to page 12, I gave you there an example where we're going to do the two methods next to each other so that you can compare them. And don't say, I'm going to do the one or I'm going to do the other. You might prefer one. But when you get into the exam, they can force you to do a specific one. So by my wording, I'm forcing you to do things a specific way. So let's take the problem up there. A man pulls a 50-kilogram washing machine. I'm going to write my 50 kilograms there so I don't have to reread. Right. 3 meters up an inclined plane. So the displacement will be 3 meters. By exerting a force of 2,000 newtons. So I'm doing 2,000 newtons up the plane. That's the applied force. And it's parallel to the plane. Now, the plane makes an angle of 40 degrees. So that angle is 40 degrees with the horizon. And the washing machine experiences a frictional force of 20 newtons. Right. So everything they gave me in the question, I put into my picture to make it easier. Right, so let's go to the left-hand side. On the left-hand side with A, I ask you to draw a free body diagram. Is that the box or the dot? The dot, right. A free body diagram is free of a body. A little bit of grade 11 work slipping in. Eh? So you have to have a dot. And now I ask you to draw a diagram of all the forces acting on the machine, but no components, right? No components, just the forces. So what do we have? We have the applied force up the plane. We have the frictional force resisting everything that is down the plane. Right, what more? Normal force, nice. Normal force is always perpendicular to the plane, right. And just remember, you may not make this into a horizontal, right? If they mark this in the end of the year and you made it horizontal, you get 0 marks, right? You have to keep it an inclined plane. If you've got problems keeping it inclined plane, make a small pencil inclined plane for you to work on if it's necessary, right? But it must still be an inclined plane. Right, and now we get to gravity. What do we know about gravity? The Earth is not pulling you sideways. The Earth is pulling you straight down. So the force by gravity will be straight down. Right, that was number A. I asked you to draw the diagram. Now number B, calculate the work done by every single force. So we have to take them separately. So let's start. And if you are working small, you can work here. Otherwise, you'll have to work on a separate page. Hey? So if you work small, you can work out the work done by friction. You can get the work done, by the applied force, the work done by friction, the work done by gravity, and also the work done by the normal force. Okay, I'm going to leave you to it, right? Work out the work done by each of those. They have to give you a mark for that. Don't start with the substitution, eh? Right, guys? Just remember, you have to check your calculators if they are on degrees. If you're not on degrees, you're going to have a problem. So you have to say shift and set up, and then check that you with degrees, number 3. Shift, set up 3, just to make sure you are working in degrees and not radians or something else. Eh? Right, so the applied force was an easy one because it was acting in the direction of the movement and the angle was 0. Right. Then friction, also easy because that's just actually always in the opposite direction. Friction is opposing movement, so it will be always 180, and that will always be cos 180 will always be 0. So that one is removing energy. And then we get to the gravity, the difficult one. So for gravity, it will be the force of gravity times delta x times cos theta. Now, they gave us 50 kilograms, so remember you have to multiply by 9,8. They're not asking mass. Some learners don't distinguish between mass and the force, right? The gravity is the force. You have to multiply by 9,8. Then it's moving 3 meters. And now we get to that difficult one, which is telling me if you understand what's happening here. Now it's moving up the plane, right? So if you have working with gravity, which is straight down, you have to turn your pen from straight down until you get to the movement. So it's that whole angle, and we said that is 90 plus the bottom angle, that is 30 in this instance. Eh? Sorry? 40. Yes. Did I say 60? Okay. At least I wrote 40. Okay. 90 plus 40. Everyone all right? Okay. And then so you can write that, or you can write cos 130. Doesn't matter. I only write cos 90 plus 40 for you to remember where it came from. Right. And then if you work that out, what do you expect? A positive or a negative value? Will gravity be helping or hindering this movement up the plane? It will be hindering, so I expect a negative. So if you don't get a negative, you have to rethink everything, hey? So it's a negative. So there you get negative 944,90 joule, I hope. Right. Everyone happy? Can I see how many minus 944,90s we got? That's looking great, guys. That's looking great. Okay, and then we get to the normal force. So for the normal force, you have N is my force. Remember, you can put Fn or whatever, just specify. Delta x cos theta. And what do we know about, I'm not even replacing that. What do we know about theta when we're working with the normal force? You're putting your pen in the direction of the force, turning it, and you're turning it 90 degrees. And what do we know about cos of 90? That is 0. Right. So now we've worked out the work done by every single force. And now we get to number C. C, I ask you, use your previous answers to calculate the net work. So I'm forcing you to work with the first method, right? So the first method was, I get the net force by just adding all the forces all the work done together. So I get the net work by adding the work done by the applied force, the work done by the frictional force, the work done by gravity, the work done by the normal force. Right, what was the work done by the applied force? 6,000. Then I get to the work done by friction, that was minus 60. Then I get to the work done by gravity, minus 944,90. And then I get to the work done by the normal force, which is 0. Now, here I'm going to show you the first thing that makes it difficult for you when you get to the memos. When you go and work through old exam papers, for instance, sometimes it looks different from yours. The Department of Education exam guidelines say if something is 0, you don't have to show it. Right? If something is 0, you don't have to show it. I want you to show it because it means you've considered it and you have decided it is 0. So you might get to the memo and that part might be missing. Right? They are allowed to do that because they say if something is 0, then you don't have to put it there. So that might be missing. I would prefer you to put every force in there because then you consider every force, right? Okay, so we're up to that one and then you add it together and you should get 4995,10 joule. If you kept numbers in your calculator, it might differ a little bit, but that's what you're supposed to get more or less. Right. Remember, you have to have 2 digits after the comma. Right. 2 decimal places. Everyone happy with this? Okay. I actually think that's the easier method. Right? No components, not difficult thinking. The only difficult thing is the angle. If you can get that angle right, then this is the easier method to use. Right. But let's go and do the other method as well. So on the right-hand side, we start once again. Draw a free body diagram of all the forces on the machine, but now I ask you to use the components. So let's do this with components. So remember to keep it inclined. So F is fine, frictional force is fine, normal force is fine. But now for gravity, we are going to split it into components. So we're working with the gravitational perpendicular to, and we're working with the gravitational force parallel to the plane. So we're splitting the single gravity over there, we're splitting up into components. Now that's grade 11, so you're supposed to be used to doing this. Everyone happy? Right, that was A. Now we go on to B. Now with B, I ask you to calculate the net force. We're looking for F net. Now, net is the answer of all of the forces together. So we look at all of the forces together. Now first, let's look at this direction. You look at the direction that's perpendicular to the plane. Now tell me, is this washing machine going up into the air or into the block? No, it's not being pulled into the block. If you look at that one, it is not being pulled into the plane, it's not being pushed up into the plane. So if you look at that direction, the washing machine is actually standing still. Right? It's not moving in that direction, it's not moving in this direction. It's standing still. And if it's standing still, which law of Newton applies? First law, right? An object will remain stationary. Right. Okay, so in this direction, there is no net force, right? That means that what's working up and what is working down is cancelling out, right? They must give an F net of 0, all right? And if something gives 0, I don't even have to mention that if I'm working the net force out, right? So I end up with only looking in this direction because all the others together gave a 0. So I only have to look at that direction. So when I work in writing down the net force, I will say, okay, let's take upward as my positive direction. And then the applied force is a positive force. So I'm using the F for the magnitude and a positive for the direction. And now I'm looking at friction. I have to add them together, but friction is in the negative direction. It's a negative force. And then I'm also adding the gravitational parallel force, but once again, it's a negative. So that negative and that negative is because it's in the negative direction. So let me just repeat, because I know grade 11 was a long time ago. Those two made 0, so I can ignore them. Now I'm looking at what's left is that. So to get the net force, the answer of all the forces, I'm going to say if it is in the positive direction, so I can take it like it is, but the other two are in the negative direction. So if I add them, I have to add negative F and negative FG parallel. Right. Now F we already have, so that's easy. I can put the 2000 in there for F. Frictional force we already have, that's minus, and that's 20. And then we get to gravitational parallel. Now, I remember grade 11 is a long time ago, so just on the left-hand side page, I just reminded you, right, if we're working on a parallel plane, we're working with X and Y. If we're working on an inclined plane, the one that's going to be split into components is gravity. And we're now looking at the parallel one. And how do I work out the parallel one? It's always the whole gravity times sine of the bottom angle. Right, so for this one, I will have the whole gravity times sine of the bottom angle. Right, and then you just have to calculate that. And for those guys who are fast, they already should have 1665,03 Newton. Okay, so is grade 11 coming back as well? Nice. Okay, let's go on with number C. Now we've worked out the net force, and what we're now going to do in number C is now we're going to use this F net to calculate the net work done. Right, so we want the net work done. Now for any W, it will be that F times delta X times cos theta. Now the net work, the net force, 1665,03, right? Then delta X, we moved it 3 meters. That is 3. And then once again, the angle might be a problem. What force am I working with? The net force. Tell me the direction of this net force. That net force was up the plane, right? It's actually perpendicular to the plane and up the plane. That was the direction of my net force. So I put my pen in the direction of the net force. How far do I have to turn it to get to the direction of movement? Nothing. So that is cos of 0. And then when you work that out, you also end up with 1995,01 joule. So it doesn't matter if you use method 1 or you use method 2. Right. So when you get to exam papers and you look at the memos, they might have done it this way, they might have done it that way. Both methods, perfectly legal. Both methods, same amount of marks. Choose the one with which you feel more comfortable. Right. So back to page 10. We are working on work. Now we've talked about the network, and we've worked out network with our 2 different methods. And now for the first time we're going to use that network. Why was it important to work it out? Because we now have a new thing that we call the work energy theorem. And the work energy theorem we can actually just remember, and it's on the information sheet as well, that the net work done is equal to the change in kinetic energy. Right. Because we said the work done. If you got a positive work answer, it meant you added energy to the system. If you got a negative answer, it meant you removed energy to the system. And now we worked out the net work, which is the total energy given or removed from the system. And you know energy can't be created or destroyed. Eh? So what happens to that energy? If you give energy to the system, what's the system going to do with it? It's going to go faster. It's going to increase its kinetic energy. Right. So the definition is easy. The net work done on an object is equal to the change in kinetic energy of that system. And this is nice because now we have a way to get to velocities. Right. If you remember kinetic energy, down here, if you can't remember, the kinetic energy is half mv squared. Old news, grade 10. Right. So you have to put it in there. But what do you have to remember about the V's? The V's over there, remember energy is just a scalar. You don't have direction. So no positives and negatives, right? No positives or negatives on this side. That velocity is just magnitudes. Not that it's ever a problem, I think. I haven't seen one where it turns around. Okay, so go back to our problem. We are back on page 13 with our washing machine that is being pulled. Now what we did with the washing machine is we pulled it up and we've now worked out the network that we did. And it was a positive. What does that tell you? That we're adding energy to this washing machine's movement. So what's the washing machine going to do? It's going to speed up, right? It's going to have an increase in kinetic energy. So now in this one I ask you, the washing machine starts from rest. What do you get from that? That V initial is 0. Right, it's starting from rest, so the initial velocity is 0. And now I tell you, use the work energy principle or theorem to prove that after 3 meters, the magnitude of the velocity, so that's now the final velocity. Right, and I ask you to prove that the final velocity is this. Now just remember, if I ask you to prove it, you may not use 14,14. Right? It should be your answer. Right. I'm asking you to prove. If I'm asking you to prove it, you may not use it. That must be your answer. You must show that it is true. Right. So you're not going to use that. That is actually what we want to work out. We want to work out what is the final velocity. And then we can use it, then we can compare it to 14,14. So I'm leaving you on your own. You're going to do this. Is the change in kinetic energy, and that change in everything is final minus initial. Right. So both of them has got a half and an m. So what we usually do is we take the half and m out, and then you end up with v final squared minus v initial squared. Right. So go on with that to show that the final velocity is 14,14. Remember to get the square root, huh? Right. Is there someone who haven't found 14,14? You happy with that one? That's easy, eh? Okay, so we'll do the last part of the question when we get to that. Just go back. We've now, on page 10, got up to the work energy theorem. So we're halfway through what you're supposed to know about work energy and power. Now, when we look at the next bit, it's about conservative forces. If you want to know about conservative forces, there's one thing in the definition when we mark the definitions at the end of the year. Time and again you get 0 for this. Because you remember things like dependent of the path and independent of the path. What is the word in that definition that you forget to write? The work done. The work done. Just highlight that because that's the word you forget. Right, so if something is a conservative force, it means that the work done by that force is independent of the path. So it doesn't matter which path you follow. And that is very nice for us to have. What is our examples of a conservative force? A conservative force, gravity, right? Gravitational force. And that is very important when we do things about work, energy, and power. So what I can do is I can ask you, I've got this inclined plane. I'm moving something that is 3 meters. That is point A, that is point B. If I ask you to move something there, I tell you it's a 10-kilogram box or whatever, I can ask you, what is the work done by gravity? How are you going to work that out? You're going to say it's the gravitational force times delta x times cos theta. Just have to give you an angle here, say 40 degrees. You can do that. We've done that now, right? But what are you going to do if I tell you, work out the work done by gravity when I move the box like this? Calculate the work done by gravity when I move the box like this. Is it a problem? Gee, if I have to work out every single little bit, that would have been a problem, right? But what do we know about gravity? Gravity is a conservative force. And what does that mean? It means that the work done moving it straight from A to B will be the same as the work done moving it all the way like that. Or if I chose, I could have moved it like that. Make that root C. Root A, root B, root C. It doesn't matter how I move it because it is independent of the path. Right. So if they in the exam ask you to calculate the work done by gravity for moving like that, you just say, I know about gravity. Gravity is a conservative force. So the work done by gravity will be the same. It doesn't matter which route you take. So I'm not going to try that. I know I can work straight because this is the one that I can do. Is that right? So what does it mean if a force is conservative? It means, most important word is, the work done by that force does not depend on the route that is followed, right? The work done by the force in moving an object between 2 points is independent of the path. So you can move it wherever, right? And then obviously the other way around. If it's non-conservative, then every single path will have a different work done. So just to use that, if you turn to the next page, down there at the bottom on page 12, I'm now going to show you 3 different methods that the teachers and the textbooks use to work out the work done by gravity. Now, if I told you there's a 10 kilogram toy car, 10 kilogram toy car, pulled 3 meters up an inclined plane. The plane is at an angle, this is very small, of 30 degrees there, and they tell you that the height is 1.5 meters. Right. The method that we prefer to use is the one in the definition, right? So one in the definition, use the whole force. So it's 10 times 9,8 to get the whole gravity, times 3 times cos, it's moving up the plane, and if it's moving up the plane, it's 90 plus the bottom angle. Right, and then you get minus 147 joule. Right, that's what I prefer you to do. Right, but what you can do is instead of working with only gravity, you can go and split up gravity into its two components. And some teachers like to do that. Right. Okay, but it's not necessary. This is actually the way that the definition wants you to do it. But if you did that, then you would have said the work done by gravity is actually the work done by the parallel component and the work done by the perpendicular component. So you are working with them separately. And then if you work out the work done by parallel, it's the parallel component, delta x, and then what would be the angle? It would be the angle between the parallel component. I don't like this because you write down two thetas and they've got different values. Right. So I would prefer never to do this. But if your teacher does this, just know where it comes from. She's working with the two components separately. But you will get the same answer if you work with them separately and if you work with the single one, which is neater actually. Right, but now we've worked with conservative forces and now we've got a third method. And the third method is the fact that it's conservative. So you can work with the movement that we are asking you, that is root A, or you could have done using a separate second root, root B. So the work done by root A, by working with gravity root A, will be the same done by gravity when you go root B. So now you've got two different parts. Now tell me, for this part where you're working horizontal, what is the angle between gravity and the movement? Cos 90. And what do you know about cos 90? 0. So this part of the movement gets no work done. The work done by gravity to move it like this is 0. I know your teachers always tell you, if you are carrying your suitcase at school, your bookcase, how much energy are you giving to your bookcase? 0. Because the force that you are exerting is upwards, but the movement is forwards, right? So you're not adding energy to your bookcase. You may become tired, okay? It's just from keeping yourself up, right? From keep exerting that force, but you're not actually giving energy to the bookcase. Right, so that part of the movement has a 0 work done. So you can actually just go and work out the work done by that. And for that one, it will be gravity delta x cos theta. Now gravity is the whole gravity. What is now my delta x? It's actually the height, right? So now delta x is that delta x, which is the height. And then cos, and now we have to think, for this part of the movement, gravity is down, and the movement is up. So you're working with 180, right? So sometimes they use that one. Everyone happy? So you now see where your textbook or your teacher come from. And they all fit together. And they give the same answer. It doesn't matter. It gives the same answer. So work with what is comfortable, but this is the one according to the definition. Right. Now, back to our first page. Page 10. We've talked about conservative forces. Right. Now, we are going to have a new form of the work done by the net force. We have our work energy principle, which says the net work is equal to the change in kinetic energy. That was up there, right? Now, sometimes we have a problem. Now, just look on the right-hand side on that page. This page 11 is where we did that inclined plane. Is it right? Now, on the inclined plane, the bottom angle was 30. Did we need that 30 when we worked out the work done by the applied force? No. The angle was 0. Applied force, it didn't matter what the bottom angle was. How about frictional force? Did we use the 30 when we worked out frictional force? No. Did we use the 30 when we worked out gravity? Yes. So it would have been a problem if I didn't have the bottom angle, right? For gravity, work done by gravity, you need the bottom angle. How about the normal force? No. So gravity is the only one that needs the bottom angle. And now, if you look on the right-hand side, if you don't have the corner, if there is no corner, right, it will be easier not to work with gravity. Right, gravity is my conservative force. So I work with all the rest. What do we call all the rest? The non-conservative forces, right. So the non-conservative forces is all the separate ones except the one done by gravity. So if there's the work for the non-conservative forces, you add all the work except the one by gravity. And that is the nice to use when the angle at the bottom corner, the angle there at the bottom, is not given. Right. When you've got no corner, no angle down there. Right. Use this one instead of the W net one. Right. Because then you don't need it. Right. Then we're back at grade 10. And now I know your teachers in school, they are very pressed for time, and it's not their fault. Your syllabus are very full, right? So they just get to this part and they say, oh, and you've done it in grade 10. Flip the page and go on, hey. Or your textbooks, they do just one example and then they go on, right? You have to be able to do this. And this is actually the easier way to do some of the questions. So let's just look at this. Mechanical energy. Mechanical energy, it's both the kinetic and the potential together, right? And then you get kinetic, right, due to movement, half mv squared, and you get gravitational, EP, mgh. Do you remember them? I hope it's coming back. Right. What's important over there is both g and the v over there has got no sign. No positive, no negative, right? Because energy is just positive. So here, don't put a negative into your velocity value, right? For velocity and gravity here, you don't have to work with positives and negatives. Right, then we get to the principle of conservation of mechanical energy. Now we said gravity is a conservative force. What does it conserve? It actually conserves mechanical energy. So if gravity is your only force, then the mechanical energy at the start and the mechanical energy at the end will be the same. There's no change in mechanical energy. Right. So then the total mechanical energy, which is EP plus EK before, is same as the total mechanical energy afterwards, both added together. And then you just have to put it in there. So this is very easy to use. Where can I use it? When you get projectile motion, it's only gravity. This is an alternative way to do it, and it's actually easier. Because with projectile motion, you have to decide, is G now positive or negative? The delta Y is difficult because it's got a direction. But you can do this, it will get the same answer, right? Just remember, they can force you to use a specific way of doing. If they say use principle of conservation of mechanical energy, you may not use equations of motion. Then you're stuck with this. So you have to have all the methods. They can force you onto a single one. Right. So we'll do an example when we get to the questions that we're going to do. I just quickly want to look at the last part, and this is back to grade 12. And that is power. Power. Now, you learned about power in grade 11 for the first time. You learned about power when we were doing electricity. Do you remember electricity? We did power, and we said the power is the work done per unit time. So then we said if you had a light bulb and your light bulb was typically 30 watts. Now remember, we measure that in watts, the power. If it was 30 watts, then it was 30 joules of light energy produced in every single second. So if I had to choose between a 30 watt and a 35 watt, and it's my study area where I need a lot of light, I go for the bigger power, more watts, 35 watts, instead of 30 maybe. Right. But it also depends on how effective it is, right? But we're now using LEDs. We're not using any more old-fashioned style bulbs usually, because they had a lot of the energy was heat. And we actually didn't want the heat. We wanted light. So we're now using LEDs. But still, if it's marked 30 watt, it means it's converting 30 watts of electrical energy to light energy every single second. Right. Now we get to work. So what is power in this context? Now, if someone's got a power of 200 watts, it means it's doing 200 joules, it's giving 200 joules of energy to the system per second. And that is just the important thing. It's in every second. And there's another equation. So this one is old news. What is new is that one. You can also work out the work done, or the average work done rather, by the force, right, and it should be a constant force, times the average velocity. Right, how do you get average? You add the beginning and the final and divide by 2, right, to get the average. So let's try and do this. Go back to the problem we're working on page 13. Right, so now on this page we've started out with all the forces working on my washing machine. I've worked out the work done, the net work. I've worked out how fast it is traveling at the top. And now I want you to calculate the average power that the man is doing. Right, the man is pulling up. How many joules per second? What is the power he's exerting? Right, or dissipating. Right, now let's look at the first one. Calculate the average power of the man with that. So, just because I know where we're heading, draw a little line and do it on 2 sides. We're looking at that one. Right, now, the power, what power? Is the power of the man. So which work done is done by the man? The man is the one exerting the force, right? The applied force. So the work done by the man is that 6,000 up there. That is what the man did. The man did 6,000. And now we get to the time. Did they give you the time? No. But if you go back to the question, what do we have? We have that they told us it came out of rest. So we had an initial velocity of 0. We also have a final velocity of 14,14. And we also have delta x. It's moved 3 meters. So what does that remind you of? Equations of motion. So now you're supposed to go to your red information sheet to see if there's a way that we can get delta t from there. So if you look at this one, we don't have acceleration. Don't go working it out. It's not necessary. You can just go and find this equation where you have the initial and the final and the delta x. We've got all those. And then we just work out delta t. So we're starting off. Delta x is equal to v initial plus v final divided by 2 times delta t. Substitute. Delta x was 3, initial velocity 0, final velocity 14,14 divided by 2, and I'm looking for delta t. So if you work out delta t, all right, 0,424 seconds or more or less, and then we're going to use it in this occasion. Right, depending on how many digits you leave in your calculator, you might end up with 14150,94 or 14140, right? It doesn't matter, they mark the whole range. So you can leave that number in your calculator with all the digits. So they will mark anything from there to there and anything in between. Right. Everyone happy? So this is one way to calculate the power. Now let's do the same thing with the second method on the right-hand side. Calculate the average power of the man with P average equals F times V average. Now we're working with the man, so which force do we need? We need the applied force of 2,000. And how do I get the average velocity? That will just be the initial plus the final divided by 2. That gives you the average velocity. And then you once again end up with 14140 watts. So both methods gave you same answer. It's nice to know, so it doesn't matter which one you use. Right. So this one you don't have funny digits, you will end up with this. With this one, depending on what you did there, you might have a little bit different answer. Right, so if you go back to page 10, just give a moment. I see there's a few calculators still effectively finding that last one. Right, so this is actually not so difficult. If you now go back to the first page, page 10. Page 10 is your summary of everything that you need to know with work, energy, and power. And we've been through it all. It's not that difficult, is it right? Do you feel more confident with this? Because now we're going to add momentum to the mix. Are you all right? Okay. So whenever you have to revise, you have to do revision on work, energy, and power, go back to this page. Because this page shows you everything you're supposed to know with that topic. Right. And then work through this one again, because this one with the washing machine is sort of covering everything. Right. Okay. So we're going to move on. And now I want you to look at page, 14. Page 14. Now we're adding momentum to the mix. Now what we like to do is, if you look at the opposite page on page 15, we're going to do this question soon. And this type of question is where they tell you things like, James Bond starts from rest and skis down 25-meter slope with a villain at his heels. The slope makes an angle of 38-degree angle with the ground. He experiences a frictional force of 10 newtons. Then at the bottom, he covers a horizontal plane for 15 seconds, experiences a 50 newton frictional force. It brings him to a parcel, 1 kilogram fixed to an inelastic rope. He grabs the parcel, he swings up, so they've got a collision with the parcel. He's swinging up, and he swings up and breaks the window, escapes through the... Okay. And immediately feel, oh gosh, hey. Right. Because the problem is, you've got different parts, right? Every single part of this question is actually a new happening. And you have to look at that. So the first part would be to say, he's sliding down an inclined plane. Right. The second part will be he's going there over a horizontal plane. That is something different. Right. Now he's hitting the parcel. So there you've got a collision. That's something new. And then he's swinging up, and that is something new. Right. So you've got 4 different parts of this question. And now the question is, which equation for which part? Right? Because there's velocities all over, there's masses all over. It's difficult to know which one. And that is what we're now going to do on page 14. So if you look on page 14 on the left-hand side, we are going to see what should I look for in a question in order to decide which equation will be best to use. And the most important thing is this a closed system or not? What is a closed system? One with no external forces, right? No friction, no applied force, no external forces, closed system. Right. So the first thing you have to look for in every single part of the question is there friction or is there not friction? Right. So if there's no friction then, and no applied force, then you are in a closed system. And in a closed system, things are contained. In a closed system, no one is having a hand from outside and adding energy, right? There is no friction that is removing energy. So in a closed system, things stay conserved. It stays constant. If it's conserved, it's not lost, right? That means before and after you'll have the same amount. So if you look at a closed system, we have conservation of mechanical energy, and we also have conservation of momentum. Right. And the moment you're using with conservation, what will be the first step? The first step we'll see if it's conserved, it stays constant. Right? So conservation of mechanical energy means the mechanical energy before and after are equal. The same with the momentum. The total momentum before and the total momentum after are equal. It's conserved. It doesn't change. Everyone happy? Now, if there's no friction, you can use conservation. Right. Now, when do I use the top one? When do I use the mechanical energy one? I use that whenever I've got something moving. Well, you have to have up and down because it's got an H in there, right? So when it's up and down, but it can be a pendulum, right? Something on a rope that's swinging, right? Pendulums. Free fall. Why can I use it with free fall? Because free fall's got only gravity. So it is a closed system. So something that I did with projectile motion, I used equations of motion, but I would have got the same answer if I've used mechanical energy. Now, also with inclined planes and curved planes. And now, sometimes this is the only way to do it. If I've got a pendulum, and that pendulum swings from there to there, they can tell me the height, right? And they can ask me, if it's starting from rest over there, what will be the velocity down there? Can you do that with an equation of motion? No, why not? It's not in a straight line, right? It's not in a straight line. So you may not do that with equations of motion. So for a pendulum, the only way to do that would be to work with energy principles, right? To work with mechanical energy. So for pendulums, I immediately go to this one because this is most probably the best way to do it, right? Or the only way to do it. Free fall. If they say in a free fall question, use equations of motion, then you're stuck with equations of motion. But if they don't say it, you could have used this as well. Let's take an example. Typically, I'm telling you I've got a ball down here that I'm shooting up with, say, 12 meters per second. It's going up, 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 and I'm asking you, okay, let's say it starts from a height of 0.5 meters. It's going up, 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 starting from 0.5, and now it goes up to a maximum height, and they ask you, what is that maximum height? Now, what would you have done with projectile motion? Projectile motion, you chose a direction as positive. First thing, you would have said, let's choose up as positive. Now, I have an initial velocity down there of 12, and it is in the positive direction, 12 meters per second. Right. What is the final velocity up there? 0. So final equals 0. Right. What do I know about this? No gravity, no air friction. So you've got gravity, and gravity is working down. Right. So now it is negative 9,8 meters per second squared. And we're actually looking for height. So I'm looking for delta x or delta y. Right. If it's up and down, I make it a y, but it's not necessary. You may use x. Right. So we're back with equations of motion. I've got the a, which is the g. I am looking for delta y. What don't I have? Time. It's easier to say I don't have time, so choose one that don't have time in there. So I'm going to say, okay, let's say V final squared equals V initial squared plus 2G delta Y. Final is 0. Initial was 12. Remember to square. Right. Plus 2 times minus 9,8 times delta Y. Now I need someone who's quick on the calculator because I haven't worked that out. First one to give me that answer. Come on. .35. Okay, 7,35 meters. Right. Is that the answer to the question they asked? No, because I only calculated that part. Right. So if I want the maximum height, I will have to take the 7.35 and add 0.5. That would give 7.85 meters. That is the maximum height. Everyone happy with this? Old news. Now we're going to say, okay, there's only gravity working on this. So immediately I may say the mechanical energy down there is equal to the mechanical energy that it will have up at the top. Right. Mechanical energy, just EP plus EK. This side was for initial, that side was for final. Right. Give me an equation for potential energy. Yes, mgh plus half mv squared, all for initial. mgh plus half mv squared, all for final. Right. And what I can even do is I can even cancel out the m's. Eh? Right. Because it's not 0, I can divide every term with that. So over here, now remember what's in this one. In this one, I have to know that, remember, we're working with energies. And then for V and G, there is no sign. So now you may not put positives and negatives into G. In this equation, G is always just 9,8. We're working with energy. It doesn't have a direction. Right? Just 9,8. What is the initial height? 0,5. Initial velocity? 12. Final, G is 9,8. We're looking for the final height, right? And what do you know about the velocity up there? 0. And then you can work out that final height. Did you check that? Happy? Right. And isn't this much easier, actually? You don't have to remember, oh, is G positive or negative? What is delta Y? Right? It's nice, huh? And something else. You have to choose from which height you're working with. In this one, I started off by saying the initial height is 0.5. Right. But you could have changed it. You could have said, okay, let's make that height 0. Okay? Then this would have been 0. But then you would have ended up with 7,35. Because then the final was also measured from there. Right. So just remember the initial and final is measured from the same height. So when I did it in blue, I measured from the ground. When I did it in red, I measured from the height from which it traveled. But then, to get the final height, the maximum height, I will still have to add the bottom part, because then it's 7,85 meters, and that is from the ground. Right. So what's nice in this one is you can choose your own reference point. And if they give the question with everything measured from the ground, work from the ground. Right? Don't go working from somewhere else if it's not necessary. Everyone happy? Is grade 10 coming back a little bit? Right, nice. Okay, so if there's only gravity, there's no external forces, you've got a closed system and you have conservation of mechanical energy. And when it's conserved, it stays constant, so you can say the initial is equal to the final. Right. But it's also true for conservation of momentum. Right, so when do I use conservation of momentum? Right, collisions and explosions, right? Any collision, any explosion, you don't even have to think about it. They may not include friction because then you can't do it. Right. So we work with a closed system. But here is the catch. What is the catch always when we work with momentum? Directions. Directions. Here you have to be very careful to put in plus and negative. If something bounced back and you don't put the negative in for the final velocity, then it will be wrong. Hey? You have to have bounce back. Right. So for closed system, you have conservations. And that's the easier one to do. Right. Now we get down to here. Sometimes it can also be elastic. A closed system is not necessarily elastic. It might be. And elastic means the total kinetic energy is conserved. Right. Now, our time is running on, so I'm going not to talk too much about this. We'll see if there's some time somewhere we can come back to this. Let's look at the right-hand side. On the right-hand side, now this you can do with or without friction. It doesn't matter. You can also do it for that one. We could have done the same thing we could have done with W net. That would have worked for this one as well. For this one, for W net, what is the only force working on this one? What's working on my ball as it's going up? Only gravity, right? So the net work is equal to change in kinetic, but the net work is only the work done by gravity, which is half mv final squared minus v initial squared. Right, work done by gravity, it's the whole gravitational force. Do I have the mass? No, so come on, just put 9,8 m in there. Times, we are looking for this traveling distance, delta x, right? Cos. Now, if I'm working with gravity, gravity is working downwards, and I'm moving upwards. So this should be 180, right? So I'm ending up with minus 9,8 m delta x. Okay, it's looking horrible. Let's see if it works out. Right. Equals half m. Okay, never mind. It will cancel out on the other side. Right. V final up there, 0. V down there, initial, 12, and remember squared. So that is minus 144, and then the m's will cancel out, and I will end up with a delta x of 7,35 meters. And then I say, okay, so that maximum height will be 7,35 plus the 0,5 below, and that will also give you some I. So there's 3 different ways to do the same question. Right. And sometimes on the memos, they forgot one of the options, and then you feel, oh, I'm wrong. Right. If there is no friction, then you may use conservation, but you may also use this. This is with or without. Right. Now say there is friction. May you use the left-hand side? No, the left-hand side is out. No friction, no left-hand side, right, if there's friction. So we have to go to the right-hand side. Now, on the right-hand side, we've actually just got 2. We've got the work energy principle, and we've got the impulse momentum principle. And then the work energy for non-conservatives, just a special way to do the W net one. So what is the difference between work energy principle and impulse principle? When do I use that one? When do I use that one? If you look at W net equals delta EK, what do we find in a W? A W has got a delta X. Right. So if they give you a delta X, then I'll go with that one. It will be the easier one. But if you look at the impulse momentum, you remember that one, impulse momentum. Fortunately, you've just written exam, so it's fine. Huh? Right, impulse momentum. if you look at the impulse momentum, what do you have there? There you have delta t. Right. So if you read your question and they give you delta x and there's friction, friction tells you I've got to be on the right-hand side. Delta x tells you work energy principle. Right. But if they give you time, then this one will be easier. Right. You can always confuse them by using an equation of motion when they give you t to get delta x and then do the top one, but it will not be on their memo. Hey? Right. So if they give delta t, do this one. If they give delta x, do that one. Right. And then if there's no bottom corner, no angle, then you just switch that on for the non-conservative forces. Right. So there's not that many. So let's go and look at our question on the right-hand side. So we're on page 15. Now, let's read slowly. The script of a new James Bond movie includes the following scenario. James Bond, 80 kilograms. Right, go and write it in. 80 kilograms. I don't want to read the passage. So he's 80 kilograms. Starts from rest. So V initial over there is 0. Skis down a 25-meter slope. What is the 25? It's the delta x over there. Down a slope, and the slope makes an angle down there of 38 degrees. And he experienced a frictional force of 10 newtons. Okay. Then at the bottom of the slope, now we're getting to the second part. At the bottom of his slope, he covers a horizontal plane, and now they give you 15 seconds. What's that? They give you a delta t. 15 seconds. And once again, he experiences a frictional force of 15 newtons. It brings him up to a parcel with a 1 kilogram, go and write it in, fixed to an elastic rope. He grabs the parcel. So what do we have there? Grabbing onto the parcel is a collision. Right. So over there we have a collision. And now he and the parcel all together swings up. Right. Now they say nothing about friction, so we can take friction as being ignored. Right. So there's no friction for that. Swings up, and now he comes up to there, and now he releases the parcel, breaks the window, escapes through the building. And to do that, he requires 5,4 times 10 to the 5 joule to break the window. And now the big question. You are the technical advisor to the producer. And you must determine if this scenario is at all possible. Okay. So what do you want to know? You actually want to know what is his velocity there at the end so that you can work out his kinetic energy. Right. Now, when you have different parts of a question, the most important thing to remember is the final velocity of that first part will be the initial velocity of the next part. Right. So you take this part and you work out the final velocity. That gives you the initial velocity for the second part. And then the final velocity for that part is the initial velocity with which that James Bond goes into the collision. Right. And then the final velocity of James Bond and parcel together will be the initial for the upswing. That's the important thing to remember. Now let's start and we look at every part of this four-part question. If we look at this first part, what's the most important thing there? Friction. Right, it's got friction. So go back to the equations. What am I supposed to do if I've got friction? I may not use a conservation. If there's friction, things are not conserved, right? I have to use one on the right-hand side. Okay. Now, in my question, what do they give you? They give you delta x. Right. So immediately, that tells you, what should I do here? I should work with the work energy principle, the work energy principle. Right. And what am I trying to do? I'm trying to work out the final velocity of this part. Everyone happy? You'll have to do it soon. Okay. Now we're moving on to the second part. What is the most important information about the second part? Friction, right? There's friction. So immediately I'm not allowed to use conservation. I have to go to the right-hand side. And what do they give you? Delta T. What does delta T give you? If it's delta T, then you're going to use the impulse momentum. So there I'm going to work with F net delta T equals delta P. Just what's very important with momentum? Directions. No? Directions. So choose a direction as positive, right? You've got a momentum. Okay, next one. We've got a collision. Immediately I see collisions, I'm going to work with what? Any collision, any explosions, conservation of momentum. Right. So for this part, I will say the total momentum before is equal to the total momentum afterwards. Right. And now I'm swinging up. Last part. I have got a pendulum. And whenever I've got a pendulum, what am I going to use? I'm to use conservation of mechanical energy. So for there, I'm going to show E mechanical down there is equal to E mechanical up there. And that gives me my final velocity up there. And then I'm going to work out the kinetic energy of James Bond and see if he's got enough to escape. Right. So it's over to you to do the questions. Right. So find out if he's going to make this. Is it going to work? Is it not going to work? Right. Show me the very first one if you've got the very first velocity. What is the velocity down at the bottom of the slope? the angle that I use for gravity? It's moving down the slope, right? So this should be 90 minus the bottom angle of 38, right? So you're going to be working there with 90 minus 38. Can I see how many of you got that right? Make it a little bit bigger. I see the guys at the back squinting. Like this? Right, important. If you start with a question, it's always good, even if they don't ask you, draw a force diagram to make it easier for yourself. So if we're looking at this part where it's moving over the ground to the right, what forces are acting on this one? Now, let's draw it quickly down there. You've got gravity working downwards, you've got the normal force working upwards, and what do you have? Friction to the left, which is very important because those two are going to cancel out. Remember, it's not going up, it's not going down. So together, those two should be 0. So what is the net force over here? It's actually that one. But remember, it is negative 15, right? The net force is negative 15. So if you forgot about direction, you put a 15 in there. James Bond would have speeded up. Right. He's slowing down because the force is acting in the negative direction. And then delta x, he is moving, delta t. Whew. Okay, sorry about that one. Okay, and the time is 15 seconds. And then change in momentum is final minus initial. They've both got the m, and it's finus minus initial. Final minus initial. Right, mass 80. We're looking for the final one. It went in there with 17,19. And then if you do that, you should end up with 14,38 meters per second when he reaches point B, just before he grabs the parcel. Right, can I see how many of you got 14,38? Yeah, good. So now we are going into the collision. Right, and a collision is always a change in momentum. Now let me just write next to this one. Okay. The total momentum before is equal to the total momentum afterwards. So it's the momentum of James Bond and the momentum of the parcel, and afterwards is the momentum of James Bond plus parcel. Right. And this is for initial, and that is for final. Right. So this will be MV, and it is for James Bond before everything. And that is the parcel, MV parcel, before. And that is M plus M for James Bond and the parcel and the final velocity. So, James Bond, mass 80, and he was traveling at 14,38. The parcel is standing still, so it's got a zero momentum. Right? And afterwards, you've got James Bond plus parcel, and they're moving at the same velocity. And then you have to work out that velocity, and that is 14,20 meters per second. So that will be, let's call it number C. That is when they start swinging up. They start swinging up with 14,20. Everyone happy until this? Okay, now the last part. Now we're swinging up. It's a pendulum, so we are using mechanical energy. Right. Everyone finished here? Can I cover this one? Yeah. Let's give a second for the guys who's writing. Let's go on. So now we are doing the swing. We're with a pendulum, and with a pendulum it will be the mechanical energy down there will be equal to the mechanical energy up there, the final one. Mechanical is EP plus EK. This is for initial, that is for final. Potential, mgh, kinetic, half mv squared. Potential, mgh, kinetic, half mv squared. I'm just going to cancel out the m. They're all the same, so I can divide every single term with that. And then what do I have to remember about g? Plus or minus? No plus or minus is in here. So this is just, he's starting out from the horizon, so the height is 0. He's starting out with a velocity of 14,20. That's what we calculated at C. And now G 9,8, and it's going to a height of 5,2. That's what they told us in the question, 5,2. And now I want that final velocity at the end of the swing. And if you calculated that, it would have been more or less 9,99 meters per second. Remember, it might be a little bit different if you round it off along the way or didn't round off along the way. Right. More or less 9,99. So that is the velocity of James Bond and the parcel up there. And now we're just quickly going to have what is the kinetic energy of James Bond up there. It's half mv squared. Half, James Bond is an 80 kilogram guy, and that is 9,99 squared, giving you 3992,00 joule. Will he make it? No. What do he need? What does he need? He needs 5,4 times 10 to the 5. Right. This is actually not enough. So, yeah, not enough. Right. Not enough. He will be banging his head against that window, and he will not be breaking the glass. Right. So he won't be able to escape. But fortunately, it's just a film. They can have someone else breaking the glass. Huh? Special effects. Right. Right. Everyone happy with that? There's a lot more questions, but our time has run out a little bit. Did you learn anything new today? Yes. Right. So if you want to go back Okay, I'm glad you found that good. Remember to go back to page 10. Page 10 is your summary of the whole chapter. And then if you want to do one good example that covers all the methods, then you go to page 13, that washing machine one. Cover it up with the paper and redo it. So then you have a memo that you can look at. Right. And then you have to go back to page 14 as well and check all the equations. So I'll see you tomorrow. Okay. Right, guys. Have a good day.